Today we are going to be talking about covalent versus ionic bonds. So we are going to be discussing the properties of bonds and how we use them to decide if they are ionic or covalent. We're going to look at the HF bond specifically and give some Lewis structures as examples. So we're going to discuss ionic bonds first, and an ionic bond is when there's a transfer of electrons between a metal and a nonmetal on the periodic table. And ionic bonds are always polar because their electronegativity is above 1.8. So ionic bonds involve a cation and an anion. So a cation is the loss of an electron. It's when an element is giving electrons to another molecule. And then the anion is the receiving molecule. And the attraction between a cation and an anion forms the neutral compound, which is an ionic compound. So when you're naming ionic bonds, you want to name the cation first and then the anion with an IDE ending at the end. The compound with the least number of electrons in its outer shell transfers its electrons to the other compound, and we will see that in a few examples on the next slide. So some real-world examples are table salt and baking soda. Those are both examples of ionic bonds. Here are some examples of ionic compounds. So first up we have sodium fluoride. Sodium is our metal in this case, and fluorine is our nonmetal. So if you look here, sodium has one valence electron, and fluorine needs to gain one. So sodium gives its electron to fluorine, and then it becomes a positively charged cation, and fluorine is a negatively charged anion. Next up, we have calcium chloride, calcium being the metal and chlorine being the nonmetal. This is how we know it is an ionic compound. So calcium has two valence electrons, and chlorines on the sides are looking to gain. So calcium is going to transfer its electrons over to the chlorine, and then you will see here that is the finished product. Last up, we have beryllium oxide, beryllium being the metal and oxide being the nonmetal. So beryllium is looking to lose two of its electrons to give to oxygen, so it passes those over, and that's our final product. Moving on to covalent bonds. So covalent bonds is the sharing of electrons between nonmetals only. They form single, double, and triple bonds because they are sharing electrons. They aren't transferring like they do in ionic bonds. These interactions happen within the sigma and pi orbitals, and also most acids are covalent bonds. There can be multiple covalent bonds within a molecule. So when you're naming covalent bonds, you want to start with the element closest to the left-hand side of the periodic table, and then the next element with an IDE ending. So we use prefixes when naming covalent compounds like mono, di, tri, and so forth. Some real-world examples you may know are water and carbon dioxide. These are both covalent bonds. Now we're going to look at how we would draw covalent compounds. So first up we have carbon tetrachloride, which are all nonmetals, and carbon has 4 valence electrons and hydrogen has 1. So when we count all of the valence electrons, put them together, we have 8 to work with. So once we draw this here, you can see that carbon is satisfied. It has a full outer shell, and then hydrogen only needs those 2, so it creates a full octet. Same here with dinitrogen tetroxide, both nonmetals, where you get to work with 34 valence electrons, and you can see here that the 2 oxygens on top have shared electrons with the 2 nitrogens. So that's why it is a covalent bond, because they are sharing those 2 electrons to maintain a full octet. And lastly, we have hydrochloric acid, both nonmetals, 8 valence electrons to work with, and hydrogen and chlorine are sharing these 2 electrons to maintain a full octet. Now we're going to look at the physical properties of both ionic and covalent bonds. So ionic bonds are always crystals. This is because of how the positive and negative charges line up within the molecule. Ionic bonds can only be solid at room temperature, and they do not conduct electricity when they're in their solid form, but they do when they are dissolved in water. So they create electrolytes. When the substance is put into water, the ions separate and become free moving ions, which allows electricity to be conducted within the liquid. They have a higher boiling and melting point, and they're very hard and brittle, so they shatter very easily with force, but they cannot be bent or deformed. Covalent, on the other hand, can be a solid, liquid, or gas at room temperature, unlike ionic compounds. They are poor conductors. They have lower boiling and melting points, and they are very flammable. One thing that is interesting with covalent compounds is they do not dissolve in water. This is because they aren't electrolytes. So we are going to look at the hydrogen fluoride bond, which is very unique because it is not classified as either covalent or ionic. One interesting thing about this bond is it melts glass, which I find very interesting. So we do name hydrogen fluoride as an ionic bond, so it's not using any prefixes when we're naming it. If you look at this image on the top, you can see that there is there's an imbalance in the electron cloud. So there's an uneven attraction between the H and the F atom. So to represent an imbalanced electron cloud, we write these two symbols on either end. So the positive one on the H end shows that the molecule has a slightly positive charge with respect to the F end, and on the other hand, when we write it on the right-hand side as a negative, it shows that on the F end, the molecule has a slightly negative charge with respect to the F end. So in the end, this bond is considered polar covalent. The electronegativity difference is 1.78, so that's what that would mean. And what a polar covalent bond is when there's a partially ionic and partially covalent characteristics within the bond, which we are seeing here with the sharing of the electrons between hydrogen and fluoride. Alright, so now we're going to look at some examples and we're going to try and determine if they are ionic or covalent. So remember, if the compound contains a metal and a nonmetal, it's ionic, and if the compound contains only nonmetals, it is covalent. So first up, we have potassium phosphate. So we look at my first image here on the left, and we can see that there's a double bond here, and there's some single bonds with them, but then we also have potassium on the outside. And potassium here is going to be transferring its electrons over to the oxygens. So overall, it is ionic because of the transfer of electrons. Next up, we have carbonic acid. So when you look at this here, you see we have a double bond. There's no surrounding atoms on the outside like there was with potassium on the previous example. So it is going to be covalent. All the elements are nonmetals, which is also an indicator it is covalent. Sulfur hexafluoride. Here you can see there is sharing between the electrons, and also they are all nonmetal compounds, which means it is covalent. Lastly, we have sodium carbonate, and we can see there is some covalent bonding going on, but there's also the sodium atoms along the outside, which are transferring electrons to the oxygens that are in need. So this is considered an ionic bond.